Okay, so as you can already see in the blackboard, uh, we are exactly where we ended our class yesterday. Okay, fine. So what we did, so let me do a quick revision of what we did in our class towards the end. So I was considering the linear homogeneous equation given by this equation, say A, okay, and we were assuming that x equal to 0 is a regular singular point for the equation A, fine. So that means we can find power series for x into px given by this. Of course, this series converges for some radius of convergence, capital R, strictly greater than 0. So similarly, this series. And then what we did, we assume that I have a series solution of this form. Is it of this form? No, it is of this form, right? X to the power m, and then this series, and going from 0 to infinity, a and xn. Is it okay? Fine. So then once we plug all three here in this equation, fine, it eventually led me to this. It eventually led me to this. Okay, fine. So now you can see the recurrence formulas here corresponding to different values of n. And when n equal to 0, the very first equation, as you know that we assume that a not equal to 0. So from here, I get this equation, and you know that that equation is called the indicial equation. Okay, and from the indicial equation, we can find out the root, and then for those roots, we will consider solutions of this form. Okay, fine. And then, if you look at the very last equation, you can see that it gives you a formula for finding an in terms of a0, a1 up to an minus 1. Okay, fine. So now let me define say f m to be simply the expression for the indicial equation. Okay, fine. So then what I can do, I can write these equations. You will see that then this expression within the bracket is simply f of, well, if I consider this one, this is f of what? This expression
f of m plus 1.
F of m plus 1. So similarly, this is f of m plus 2, and the last one, this one within the parenthesis is f of m plus n. Okay, fine. So now let me just simply replace them. So this is f of m. This is a1 f of m plus 1. Then a2 f of m plus 2, and here your an f of m plus. Okay, fine. So now if I have two distinct roots of this equation f of m equal to 0, say suppose they are m1 and m2, so definitely I should get a solution of this form. Say suppose I am considering m equal to m1, I'm definitely going to get a solution of this form. Okay. Now the question is whether for the corresponding to the second root m2 also, I can get a series solution of this form or not. Okay. So now let me again get back to these equations. So as you can see that since a naught not equal to 0, I have already told you that a naught is generally taken as 1. So then from this equation, I can get a1 in terms of a naught. So that means I have been able to find out both a naught and a1, and then from this equation I'll be able to find out a2 in terms of a naught. A naught and a1 here, and similarly from the last one, an in terms of a naught, a2 up to an minus 1. Agree or disagree? Yes? Do you agree with me, whatever I have told just now? Like say
Yes,
successively, I will be able to find out the coefficients. I mean a naught, a2 up to an. Now, here's the problem. Okay. Now, you simply look at this expression. And for that matter, look at this equation. Okay, look at this equation. So here, I don't know what is the form of m. You please don't assume that m is always going to be an integer or something like that. Okay, say I have assumed that those m1 and m2 are real, but they can be complex also, because we are not going to deal with the complex thing, right? So we are going to deal only with the real thing. Okay, but m1, m2 being real doesn't necessarily mean that they are going to give me only integer values, right? Okay, so they can be fraction. But one thing is sure, whatever may be the values of m1 and m2, you know that this n is an integer, right? This n is an integer. To be precise, when n is not equal to 0, it is a positive integer. Is it okay? And say, like, because I already know that a naught is not equal to 0, I am interested only in finding out a1, a2 onwards, right? So basically, that means here n is going to be a positive integer. Is it okay with everybody?
Yes, sir.
Yes, sir.
Right?
Yes, sir.
So now, what is going to happen? If you look at this, f of m equal to 0, it has root m1 and m2. So what is the meaning of that? What is the meaning of that? So that means f of m, it can be expressed in terms of m minus m1 into m minus m2. Is it okay? Fine, right? And obviously, if m1 and m2 are roots, so definitely f of m1 equal to 0 equal to f of m2. Is it okay with everybody? Fine. Okay, fine. So now what is going to happen? Like suppose, let me assume that your m2 is less than equal to say m1. M2 is less than equal to m1, right? So suppose we have already found out the series solution corresponding to m1 in the form say something like anx to the power n in this form, right? So then what we are going to do for the second root m1, then again, second root m2, then again I am going to follow the same procedure, right? I am going to follow the same procedure. My first equation was your a naught fm equal to 0, right? So I'm going to follow the same procedure for the second equation, right? It will be something like that, and eventually it is going to be something like this. Is it okay? Fine. Now, see, now if m1 minus m2 is equal to 0 or a positive integer, right? So suppose that positive integer is something like n. So that means your m1 equal to m2 plus n, right? So now, in this way, following this procedure, if you are going to find out the successive coefficients, like say a0, a1, a2, a3, etc., eventually at one step, for the positive integer n, in a certain state, you are going to encounter this term. Are you getting my point? Right? And what is m2 plus n? m2 plus n equal to simply m1, right? But we know that m1 being a root of the initial equation, your f of m1 equal to 0, right? Is it okay with everybody?
Yes, sir.
Right? So that means I have a problem with this equation. When the difference between m1 and m2, of course I am assuming that m1 is greater than equal to m2, when the difference between them is a positive integer, then I am in trouble. Okay? Is it okay with everybody? Right?
Yes, sir.
Fine?
Yes,
Fine.
sir.
So that means whatever approach we have taken so far, like by assuming that xpx and x squared qx, them to be analytic about x equal to 0, and then again I'm using a Frobenius series as the series solution for the given differential equation having a regular singular point at the origin. That is going to work only when the difference between m1 and m2 is not an integer. Fine? Okay? So that is going to work only the difference between them is not a positive integer. Okay? So now we are going to consider all those cases. But again, let me tell you that we are not going to get a definitive answer to that. We will be able to make some conclusion, definitely through some observation. Definitely, we will be able to make some conclusion, but it is not kind of a universal rule that is going to be. That is going to be true. Okay, but in certain cases, definitely we are going to get some conclusion that you can always use for certain cases. Okay, fine. So now, just another thing I want to tell you is that okay, let me. See, in yesterday's class, I think when I was working with this one, your xpx into y prime. So somewhere there, an because there was something like eventually this led me to that there was some term like an your nan x to the power n, okay, and then the second series pn x to the power n and going from 0 to infinity and going from 0 to infinity. So I forgot to write this x to the power n here. Please have a look at my video, and probably you have already figured it out. Okay, so there was an x to the power n because immediately after this I had written something like, and then in terms of, I mean, k equal to 0 to n, so an x to the power n. So you may have some confusion. So this was missing. I missed this, but probably you have already figured out. Okay. And another thing I want to tell you is that yesterday when I told you about the rationale behind choosing Frobenius series as the solution for second order linear differential equation having regular singular point at the origin. So then I told you that probably when the initial equation is going to have equal roots, then I am going to have something like C yn y1 ln x as a part of my solution. I should have something like this. Again, I am going to come back. I'm going to have a solution of this type. But remember, whenever we consider a solution of this type, it is going to be valid only when x is greater than 0. Okay. Now you may be thinking, what happens when x is strictly less than 0? So in that case, what we are going to do, we are simply going to make use of a transformation, something like x equal to minus t, and apply all the procedure that we did earlier. Is it okay? So that's what we are going to do. So now let me show you. The theorem. Let me just show you the theorem, and then I will. So this is the theorem corresponding to a series solution about regular singular point. Okay, so let's read it out. Assume that x equal to 0 is a regular singular point of the differential equation 1. So that is simply differential equation 1 is simply y double prime plus pxy prime plus qxy equal to 0. You already know it. And that the power series expressions 3, and in power series expressions 3 of x px and x squared qx are nothing but you already know. I mean, Pn x to the power n and Qn x to the power n. And they are valid on an interval mod x strictly less than r, okay, which r greater than 0. And again, if the initial equation, you already know what the initial equation is going to be. If it has roots m1 and m2, with m1 less than equal to, m2 less than equal to m1, then the given differential equation, it has at least one solution of the form 6. Okay, fine. On the same interval, on the and here interestingly, see radius of convergence earlier it was capital R, and for the series of xpx and x squared qx, we considered the whole interval ranging from minus r to r. Okay, but here you can see that they are taking only when 0 less than x less than r. This is because whenever you rope in that log x term, you are going to have a problem. Okay, fine. So, and where a and are determined in terms of a naught by the recursion formula 4. Recursion formula, whatever I had written at the very beginning in the blackboard today, those are nothing but the recursion formula 4, with m replaced by m1, and the series a n x n converges for mod x strictly less than r. And again, remember, they are saying that they are playing it safe for the time being. Furthermore, if m1 minus m2 is not 0 or a positive integer, then equation 1 has the second independent solution. And remember, you'll be able to use 7 as the second independent solution only when m1 minus m2 is not a positive integer or m1 is not equal to m2. Only then you are going to have two independent series like 6 and 7, remember, on the same interval, where in this case an are determined in terms of a naught by formula 4 with m replaced by m2, and again the series an x to the power n converges for log x strictly less than r. I think there should be one more, just a minute, there should be, okay, fine. Again, this theorem is playing it safe for the time being. I'm going to show you another page later on. Let me work out something. Okay. After that, I will arrive at that. Okay. Fine. So now let me just. Okay. So here, let me try out the different cases. Okay. Case one, and of course I am assuming that the initial equation has two roots, m1 and 2, and I am assuming that m1 is less than m2 is less than equal to m1. So case one, what is going to happen? I mean, if m1 equal to m2, m1 equal to m2, definitely you won't be able to find out. A second formal series. But just wait for the timing. Please don't think that I'm not going to do anything when m1 equal to m2. I'm going to do something about it. But for the time being, let me tell you is that formally you won't be able to find out the second series solution. Okay, fine. So this case, again, we are going to come back to this case later on. So now case two, when your m1 minus m2 is equal to n, where n is a positive integer. Okay. So then what happens? Okay. So now, if you recall, what was happening, my recursion formula. If you recall, my recursion formula, I'm just directly going to plug it in an or even an f of n plus n, and then your a naught m and eventually a n minus 1 m plus n minus 1 your p1 plus p1. This is equal to 2. Okay, no problem. This is equal to 2. I don't have any problem at all here. Okay, fine. So now let us assume that we have already found out the series corresponding to your M1, right? And now I would like to move over to what happens.
Excuse me, sir.
Yes.
We are not able to see the blackboard.
Oh, okay. Sorry. Okay, fine.
Yes, sir.
Okay. So basically, case one is when M1 equal to M2. I have already told you that formally you won't be able to find any a second series solution. So case two, your M1 minus M2 equal to n. We are assuming where n is a positive integer. Okay. So then, if you recall, this was my reference formula. This was my reference formula for finding out the coefficients. Okay, fine. So now, what is happening here? This recurrence formula, I can write it something like this. I can write it like this, isn't it? Which is going to give me the value of an in terms of the previous coefficients. Is it okay? Fine. Okay. So now, because I have already found out the series solution corresponding to M1, right? Now I am moving to M2. While moving to M2, ultimately, after finding out A1, A2 up to say an minus 1, I am arriving at this step. Okay, so this equation is going to be something like this. It is going to be something like this. Is it okay? Fine. Up to this, it is okay with everybody? Fine?
Yes, sir.
Yes? Okay. So now, what is happening here? Because I am assuming that your M1 equal to your M2 plus N, and I already know that M1 being a root of the initial equation, f of M1 is already equal to 0, f of M1 is already equal to 0, definitely, this term is going to give me 0. Whatever happens to the other terms, that is going to give me 0. Is it okay? Fine. So now, what is happening? You have here a left hand side which is 0, but right hand side, I'm not sure what is going to happen to the right hand side. I mean, if you plug in all the known values here, and I am assuming that a naught up to a n minus 1 is already available at my hand, it may so happen that your right hand side may not be equal to 0. Right hand side may not be equal to 0. Right? So in that case, we have a problem. We cannot go further. Okay? Right? Second series solution is definitely not possible. Or, like say, obviously what we can do something out of the first series. We can do something out of the first series.
Sir,
Yes. Yes.
can you please repeat the last step?
Repeat the last comment, right?
RHS
Okay.
is not equals to 0.
Okay, fine. See, now from the recurrence relation, I have found out this. Okay, I have found out this. So it may so happen that, like, obviously this one is 0. Obviously this one is 0 now. Isn't it? See, what was happening, that the equation that you got f m2 plus n plus all these term, you got it as a balance of some terms, right? Isn't it?
Yes,
Here
sir.
you have some value of a n, right? And if say this is not equal to 0, you have some values of this, and then that value would have negated all the other terms to get you 0, right? Now what is happening? Because I am assuming that the difference between the roots is a positive integer, right? And of course of the fact that now my m1 is equal to m2 plus n and f of m1 equal to 0. This term is always going to give me 0, but I am not sure what the other terms are going to give me, right? So in that case, if they don't give me 0, then I have a problem. I cannot proceed further. Okay, but if they give me 0, then what I can do, like say, suppose the right hand side, this is giving me a 0. Okay, so then what is going to happen? Because this is already 0, right? I have infinite choice for a n. Is it okay with everybody?
Yes, sir. Yes.
Right? So what I can do? I will go for the immediate. I will go for a n equal to 0. A n equal to 0. So then what is going to happen? Now, next term here, if I go on, I mean finding the recurrence formula. So my next, it would have been something like this, isn't it? M by m. So this is going to be, I think, it is going to be something like that, and eventually something like that, something like this. Okay. So then what is going to happen? say up to here an minus 1 into something, and then next time with this. So from here I am going to get 0 because I am assuming an equal to 0, right? And an plus 1 I'll be able to find in terms of all the other terms like a naught up to an minus 1, right? And I can follow that procedure, and continuing that I will get all the other coefficients, right? So that is going to give me a solution. Okay, fine. Now, like
Sir, why
say,
an is 0?
no, I have chosen it to be 0. I could have chosen it to be anything else. I could have chosen it to be anything else. Okay.
Okay.
Fine. I could have chosen it to be anything else. Okay. What I want to tell you is that, I mean, when both the like say left hand side is already 0, I don't have any doubt about it. When right hand side is also 0, I can proceed towards finding a series solution. Okay, power series solution. You are still not convinced. I'll come to that. Don't worry about it. All the possibilities. Next, I am going to take one example, and after that, everything is going to be clear to you. Okay. So what I'm going to do, again, I'm going to take one example. But this example again, this is a general kind of analysis. I'm not going to take a fixed example. Let me tell you what I'm going to do.
Sir, if right hand side be 0, then right hand side function has a root m1.
No. We have already assumed that m1 is already a root.
No, an f of m plus n, that is m2 plus n, equals to some function of m. So when we are putting this value of m2 means f of m2 plus n, then this is being a 0. This is the root of this function.
No. You are see, this is not f of m2 plus n. That is different. F of m2 plus n was different. That involved p naught and q naught.
Oh, right.
Okay, fine. That was different. Okay. So, okay. See, the next part of the analysis is going to be very tedious. Let me warn you in advance. Okay, fine. Okay. 2 plus 1. Just one assumption here is good enough. Okay, fine. So now let us assume that my m1, m2 are the roots of the initial equation. So that means your f of m. So this is, as if you recall, f of m. This was your okay, plus q naught, okay, and since m1 and m2 are roots, so definitely what is going to happen, your m minus m1 into m minus m2 is given by this. Is it okay? Fine. So that means your m1 plus m2, this is what? This is going to be minus p naught minus 1. I'm not bothered about what is m1, m2. So I'll be requiring only m1 plus m2. Is it okay? Fine. Okay. And again, let us assume that m2 is less than equal to m1. M2 is less than equal to m1. Okay. Fine. And Now again, let us assume that k is an integer such that k equal to m1 minus m2 plus 1. Okay, so basically what I want to tell you is that if m1 equal to m2, then k is going to be equal to 1. Is it okay? Is it
Yes.
okay? Fine.
Yes.
And again, please remember that here this analysis I am doing assuming that m1 minus m2 is an integer. Okay, either it is 0 or a positive integer. Is it okay? So that is what I am doing. So now, can you give me now k in terms of m1 and p naught? So if I assume k to be this, so then this is going to be m1. Say if you transpose m2 towards the right hand side, minus m2 is going to be plus m1 plus p naught minus 1, isn't it? And then this is already there, and so 2m1 plus p naught. I have a specific purpose behind this. Okay, I'll tell you what it is. Fine. So far so good. So I will be requiring this one later on. I will be requiring this one later on. Okay, fine. So now let us assume that the series solution corresponding to the root m1 is given by this y1 equal to, say, this one. Of course, here a naught not equal to 0. Here, assuming that. Okay, just a minute. I would like to do. Okay, I mean once I reach there, I'll let you know. Okay. So now, what we are going to do, like you already know in our earlier studies of finding roots of second order linear homogeneous equation, what was that? If I already know a solution, if a solution is already known, the second solution, of course, I mean linearly independent solution of that pair of fundamental set, it can be found out by plugging in y2 equal to v y1, right? Where just a minute, let me just erase the code for a moment. Where what was happening here? Where your v prime is equal to 1 by y1 square and then e to the power what? E to the power what?
Minus integration p of x dx.
Dx. Okay, fine. Okay. So now, if you recall this one, see xpx was p naught plus p1x, say p2x squared, etc. Is it okay? We already assumed it to be of that form, isn't it?
Yes,
Fine?
sir.
Yes. So this implies your px is going to be and so on. Is it okay? Fine. So that is why here for the timing, let me write it as this only. So this minus it will be fine, and then you will say this is going to give me e to the power minus p naught ln x, and then e to the power say minus p1x. I'm not even bothered about it. Is it okay? So far so good, right? Yes? Fine? Okay. So now let us look at this term. This is simply your just a minute. Y1 squared. Okay. One thing I sorry. Just a minute. Let me again reiterate. See what I did. I told you that y1 is this form. No, y1 is it will be of this form. Is it okay with everybody? What mistake I did, right? Is it okay?
Yes.
I think x to the power m1 was missing. Fine. Okay. Now you got the mistake. What mistake I did? Fine. Okay. So then for y1, what I'm going to do, it is going to be x to the power 2m1. Okay. And then simply it is going to be a naught a1x this whole square. Okay. Then from this term, it is going to be your x to the power minus p naught. Okay. And then let the remaining stuff be here. I am not even bothered about that. Okay. So far so good, right? Yes. Up to this, is it okay?
Yes, sir.
Yes, sir.
Right?
Yes.
This is simple calculation. So now let us see how we are going to manipulate it. I am going to bring this p naught here. So then this is going to be fine. Is it okay?
Yes, sir.
Yes.
Right? And what is 2m1 plus p naught equal to?
K.
K. Fine. For me it is easy, but for you again you have to. This is K. Fine. So now let me concentrate here. Let me concentrate here in the remaining part. Let me concentrate here in the remaining part. Okay. See, now obviously this is the numerator is non-vanishing. Is it okay? And then again you can see that the denominator it is analytic at x equal to 0. Isn't it? It is analytic at x equal to 0. Is it okay? Fine. Isn't it? Since the denominator is analytic about x equal to 0, and so is the numerator, right? So definitely, what I can do, the expression within the, blue boundary, I can express it as a function of x, which is analytic at x equal to 0. Is it okay with everybody?
Yes, sir.
Yes, fine. So what I'm going to do, I'm going to write it as some function g of x. And of course, just a minute. Here, I'm going to okay. So I'm going to write it as something like, so this is equal to your 1 by x to the power k g of x, and of course your g of 0, you will see that is 1 by a naught square, and this is not equal to 0. This is not equal to 0. Okay, and basically what is happening? So that means if I assume your gx to be equal to say b0 plus b1x plus b2x squared, etc. So definitely your b0 is not equal to 0. Isn't it? Because b0 will be given by plugging in the value x equal to 0 there in gx. Is it okay?
Yes, sir.
Fine. Now, the next part is crucial. Next part is crucial.
Excuse me, sir.
Yeah.
I have a doubt. You in the expression of x px, you just divided that term by x to get p. So when you have raised e with integral px, the second term in your third line of the board, in the second term, there should not be p1x. It should be simply minus p1, isn't it? Because you had divided that by x. Or it's after
I have
the.
integrated that.
Okay.
Okay.
Yeah. Okay. Thanks.
I sometimes these kind of things happen. Okay, fine. So, so that means what I can do now. Okay, fine. So that means I can write e prime as your x to the power minus k. This is gx. So this is equal to x to the power minus k. Say b naught. I'm going to expand it a bit. Please bear with me. Just one more term. Fine. So let me write it as is it x? No, this is simply a, and so on. This is important. That is why I'm expanding it so that you don't have any confusion later on. Okay, fine. So now let us integrate it. Let us integrate it. So that means your v is going to be equal to what? Yeah, v is going to be equal to what? Your v naught just a minute. So just before this, I am going to have b k minus 2 x to the power minus 2, isn't it? Right? So just a minute. Yeah. So this is going to be what? This is going to be
minus x.
minus x. Okay. So then this term is very, very important. Fine. This term is the most crucial term. Okay. And probably by now, I mean, you have understood why. By now, you have understood why. Okay, fine. So, therefore, your y2 was what? y1b. So, if I multiply it by y1, what I'm going to do here, see, this is. Don't worry, everything we are going to do it systematically. It looks labyrinth. What I'm going to do, firstly, let me write down this term. Okay, so this is equal to your b k minus 1 y1 ln x. Okay, so then what I can do, let me write down the remaining term, like y1 is c x to the power m1, and then what, your summation, your, or maybe okay. Let me expand it so that so then let me write it like this. Just I would like to bring something here. Yeah, fine. Okay, so from here, what else can we get? Can you check? What else can we get? Do you recall the definition of K? Right? So M2 is M1 minus K plus 1, right? Okay?
Yes, sir.
Yes? Okay. So now see what is happening. If I absorb this one here, because M1, right? M1 minus K plus 1. So minus K plus 1. So that means there will be nothing. Here there will be simply X and so on, isn't it? Fine?
Yes, sir.
Yes, yes. You please just after the class sometimes you just work out at home. You will see that. And anyway, this I have taken from Simon's book. Everything is there. Although he hasn't explained all the steps. Fine. So now what I mean to say is that this again going to give you something like your y1 ln x plus this is simply your m2, because from here you can get this to be x to the power m2. Now again here you will see that this is nothing but the product of two power series. Okay, and because we have already assumed that A naught is not equal to 0, we have seen that B naught is also not equal to 0. Then what is going to happen? What is going to happen? Like this, I can write it as something like Cn x to the power n. Right? Convinced or not? Not yet convinced? I still have to figure out some stuff from here. Yes.
Sir, where K belongs to?
No,
Uh,
no, K is an integer. K is an integer.
okay.
K is an integer. Okay, K is an integer. Fine. Now, just one thing. It is very important. Later on, I'm going to do Basel. Okay. Now, please, for the time being, don't ask me anything about this time. I'm going to come back to this because if you ask me some question about this for the time being, you will get confused. See, of course, this one, it has come from the original series, that GX that we did, right? It came from GX. So now you simply look at when M1 equal to M2, right? So in that case, your K becomes equal to 1, isn't it? K becomes equal to 1, right? Is it okay?
Yes, sir.
Right? So then what is going to happen? This is going to give me, this term is going to give me B naught, your Y1, ln x, B naught, right? Isn't it? Is it okay with everybody?
Yes,
Yes.
sir.
Right? So then what is going to happen? We will not consider this term at all. We will not consider this term at all. Because anyway, for k equal to 1, that term is not defined. Because that B naught will be absorbed with this. This is not going to be present there. Are you getting my point or not? So in
Yes.
that case, right? So in that case, what is going to happen? In that case, what is here when when your M1 equal to M2, when M1 equal to M2, then your K is going to be equal to 1. So K minus 1 is going to be equal to B naught. So in that case, what is going to happen? Your Y2 is going to be this B naught, Y1 ln x. Of course, this B naught also I can change. Don't worry about it. So then this series, what is going to happen? This series is going to start with something like your n equal to 1 to infinity. N equal to 1 to infinity, something like, say, it is going to be something like this. Okay, it is going to be something like this. So that is why generally what they do, like they don't even write this term V naught, because eventually you are going to express a general solution in terms of a linear combination of both this Y1 and Y2. Now that tells you that your what is going to happen? The logarithmic term is definitely going to be present when your M1 equal to M2. When the roots are equal, definitely you can get a solution of this form where the logarithmic term is present, right? Now, it may so happen when M1 is not equal to M2, it may so happen that this one, your B K minus 1 equal to 0. it may so happen that bk minus 1 equal to 0, because this was nothing but the coefficient of ln x, so the logarithmic term will be absent in that case. Okay, and if this is not equal to 0, the logarithmic term is definitely going to be present there. But the bad thing is that we don't have any specific way of finding those coefficient, bk minus 1, all those stuff. It is, there is no general way. It is going to depend upon the differential equation that is going to be provided to you. Is it okay? Yeah, if you have any questions, just let me know. Yes.
Sir.
Yeah.
So where we get the relation of like k equals to m1 minus m2 plus 1?
No. That at the very beginning I assumed that. At the very beginning I assumed that k equal to m1 minus m2 plus 1. So basically I assumed that when for equal roots of the indicial equation, k will basically I am defining k as an integer so that you know that the difference between m1 and m2 is an integer. Okay, positive integer to be precise. Plus 1 is because of that. Because I have already assumed that m1 is greater than equal to m2, right? Okay,
Yes.
when m1 equal to m2, k is simply 1. When it is not, it is going to be another, positive integer. Okay?
Yes,
so
sir.
at the very beginning we assumed that. At the very beginning we assumed that. Okay? So now, how much time do I have? Okay. I have another 14 minutes, right? What can I do in 10 minutes? Okay, fine. So,
Sir.
this, yeah, somebody wants to ask something?
Sir, in last line, n equal to 1 to infinity or n equal to 0 to infinity, by 2 equal to in last line?
Last line, according to me, when they are going to have infinite, the m1 and m2 are going to be equal. So, according to me, this should start from 1. Okay, although then, okay, otherwise we can do one adjustment. I simply write it as this, but then I'm going to write C1, C not equal to 0, C not equal to 0, because this term, this one, it will be coming from the original series, isn't it? That bk minus 1 term, it will be coming from that, right? And that is already been absorbed with this one. That is already been absorbed with this one. You please, check it at home. I'm almost sure, 99% sure that it should be this. Even if it is 0, then this C naught should be 0. C naught should be 0. You can consider one example and then check, with the series at your hand. Okay, by multiplying all those terms. According to me, it should be. Like say, when your m1 equal to m2, only in that case, right? Say when this is not equal to 0, bk not equal to 0, when m1 not equal to m2, in those cases, when m1 minus m2 is a positive integer, then if bk minus 1 not equal to 0, then what is going to happen here? I can simply write it as bk minus 1 this, and I don't have to write anything like this. It will simply go like this. That's okay. So that is why for a general solution, they write it as this. Okay. Now, say this is for a general. This is for a general case. Okay. And you know that if bk minus 1 equal to 0, this term is not going to be there. Okay. So in case bk minus 1 is not equal to 0, this is always valid. But how are you going to differentiate the cases when m1 equal to m2 and when they are not equal, right? So according to me, in that case, this is going to start from n equal to 1 when m1 equal to m2. Okay, I think see, there are many ways through which you can obtain, Bessel's function. Okay, Bessel's function of zeroth order. One of the ways I am going to show you. So over there, you are going to see that only when this C naught is equal to 0, when both the roots of the initial equation are equal, only then the Bessel's equation of Bessel's function of second kind is going to work. Okay, and just a minute. And again, you can see that in that case, this x to the power m2 when m1 equal to m2, this is going to reduce to m1. Okay, this is simply going to reduce to m1. Okay, so next, I don't know whether I will be able to finish that.
Sir, when k equals to p be a positive integer, then this will start from n equals to 0 to infinity, then c0 to cp minus 1 will be 0.
C0 to
cp minus 1.
p minus 1.
I am taking k equals to p for a general case. Because in this series we got this type of term, something by
You are talking about
minus
the
k plus
way
1.
Gx, right?
Yes.
No, I have to figure it out. Maybe you have computed it, but I'll have to compute it immediately. I don't want to answer that.
So particularly here we are taking k equals to 1. So it is happen that k may be 2, k may be 3, 4, it may be happen anything.
Yeah, sure.
So then I am taking for general case when k equals to p, then what will happen? Means those C naught, C1,
I don't think some other, some terms, certain number of terms are going to vanish. I don't think so, because what is happening, say, if you recall, I had something like this, like whatever may be here. I had something like this. Please don't think only about the first term being absorbed with only this term or something like that. Okay, or like say here x to the power, I think m1 was there, so I absorbed with that. You still have some terms you have to multiply with the different powers of x, because basically I have something like this. I'll tell you. I have two series. Like say c1 x to the power n, dn x to the power n. Okay, so I am getting a common series like this. I am getting a common series like capital C and x to the power n out of this by multiplication by term. Okay, so you may be correct. I'm not saying that you are not correct, but probably you are thinking only about a few number of terms. Okay, because you have to adjust with all the powers of x. In that case, I'm not sure. Certain number of terms are going to vanish. Okay, you just check. I don't have any concrete answer till now. I'll have to figure it out. Okay, fine. How much time I have? So one thing. So your exam is on 17th. It is going to be from 12 to 2. So what I request you is that, you try to upload in Teams. Of course, if you fail, then you can send it to me through email. But I prefer it to be uploaded in the Teams app. So definitely, I think Teams app is going to give you a confirmation whether it has been uploaded properly or not. Okay. And anyway, if I don't see your answer script there in Teams, I am definitely going to alert you about it so that you can send it to me through email. But you don't send it to me through email unnecessarily. I'll be checking it immediately. If I don't get it, I'm going to let you know. Then you send it to me. Okay. And the second thing is that please try to convert it into a PDF. It is easier for me. It is easier for me to take printout and evaluate your answer scripts. And the third thing is that I have seen in couple of number of cases that your that pages are they're not numbered. Not numbered in the sense that if they're in sequence, it is fine. But I have seen that many cases, they're not in order. So again, I have to make another JPEG file or PDF, and then I'll have to do all this stuff. Okay. So next time, please be careful about it, and try to do as many problems as possible from CMOS. Okay, whatever chapter I have covered, try to do as many as from them, and I think they're good enough for you to do well in your next exam. Okay, so I'm going to call your next exam as mid-sem. Okay, if you still have any question regarding that, you can ask me. Yes. Otherwise, I'm going to wind it up.
Sir, is it possible to use this method in nonlinear equation?
No. No.
So,
Nonlinear is different. No. Only in certain number of cases. No, general comment, nobody will be able to make. Nonlinearity is completely different thing. Okay, it's a completely different.
Sir, what is the pros and cons of this method?
What is the
pros and cons of this method?
Pros and cons you have already seen that nearby singularity you have some problem. Okay, it still shows you some way to get something nearby this singularity. That is a pro. But the con one thing I can say is that it is too laborious, right? It is too laborious. And again, only when you have, certain radius of convergence, only then it is going to work. But again, like say, next time I'm going to do Gauss's hypergeometric equation. So you'll be able to see that this approach, this power series approach, it simplifies a lot of stuff. Particularly all the spatial functions. They can be, computed using. I'm not saying that only one particular methodology, but maximum 2-3 methodologies. If you know, you'll be able to, work with all the spatial functions. Not all the spatial functions, but the spatial functions which are very frequently used in science and engineering. Okay, so those are the pros and cons. Immediately that comes into my mind. Okay, so I think I'm going to wind up my class today here. So I will meet you tomorrow.